Okay, we're talking about some sample problems from your 4.5 where you're solving various types of log or exponential equations. And here we have a problem, sample problem, where you have log written in the problem once. Usually that denotes that you're going to need to take it out of log form into exponential form. So rewrite it when you only have one log. Usually you'll take your base, raise it to the answer, which is the exponent, equals the argument. So out of log form, we would write this as base 4 raised to the second equals the 4x minus 6. And then we can do kind of an old algebra. So 4 to the second is 16. And so we have a linear equation here to solve. Move the 6 across the line, makes that 22. Divide by 4. And our answer is 22/4. And I would probably just leave it, actually I'd probably make it 11 over 2, reduce your fraction, but leave it in proper form. Okay, the next example I have for you, we have log in the problem. We have log written twice. So usually if you have expanded log, you need to condense it down to one logarithm with the log rules. When you say plus in expanded form, that means times. If we see minus, we'll see that later, minus means divide. But these are like base logs, and if you are working with like bases, you can use these rules, exponent rules, log rules, both kind of preface that you need like bases to proceed, and we do. So we've got this log base 4, then we can take their arguments multiplied together. So again, add means multiply in exponent form. So into one log form, and it looks like I just now we take it out of log form, saying this exponent equals this argument. So move it out of log form. 4 squared equals x minus 6, and now we've got some old algebra, what we've done in our past chapter. We can reduce this to 16, distributing your x here, and we see we've got a quadratic equation. So quadratics, we get to one side equal to 0 in standard form, so bring the 16 across. Set it equal to 0, that's standard form for a quadratic. Then you can factor it or use your quadratic formula. If you prefer, that formula always works. But this does factor down, giving us two solutions of positive 8 and negative 2. Now, remember with various types of equations, we should probably always check our answer, but with some types of equations, it's critical because there's reasons like that potential solutions may not work because of a negative or a denominator issue or radical, it's not in the domain or something. So we should check our answers. I'm kind of lazy about it sometimes, but in these you must check your answer. This negative 2 is not going to work. When I plug that in for the x's to check and see if that's true, I try to type that in my calculator. When I type in log base 4, which I'm going to have trouble typing in log base 4 anyway, directly, unless you have that subscript button. Most calculators don't do log base 4, so I'll have to use change of base rule and do log negative 2 divided by log 4. Remember, if it's not base 10, you can't directly use your log button. So I'll type in log negative 2 divided by log 4 equals, and it gives me an error reading, and it should. If I were doing, even if that were a base 10 log, a regular log, common log, and I typed in log of a negative number, log of negative 2, I'm going to get an error reading. You cannot take the log of a negative number. There's no base raised to any exponent that will equal a negative number. And you know, when you graphed these back in a former section, you saw that that was also true, that there was an asymptote involved in the graph because you could not take the log of a negative number. X could not be a negative number. So the y-axis, was asymptote, not cross the y. If you remember that in standard form, the log graph looks like this. Right? That y-axis is an asymptote, meaning the graph gets close and close to x equals 0, but it never touches it, and it definitely doesn't go over here. So that's why the argument, the x part of the log part, the x part cannot be a negative number, nor can it be 0. If we try to do log of 0, and this is non-shifted, just in standard form like we're doing here, we also get an error reading. So that's the issue with that. So anyway, we cannot use a negative number 0 as the argument part. So the negative 2 cannot work. Check out 8. 8 is fine. If you plug in 8 for these x's and check your work, you'll see 8 works. So our only answer we should plug in is just the 8 for the solution set. All right, next example. This one has a log in expanded form, but it's also on each side of the equation. Let's see if I can get my act together here. Okay, so here's a sample problem. So I'll do the same thing I just did on this side, condense it down. It's in expanded form with the plus sign, so I should condense that plus 2 times. Again, these are like base logs because these are base 10s. Since you don't see anything else, those are base 10s, understood. So we can rewrite it as a base 10 log and plus becomes times. The other side does not have any expansion, just log of one number. But here's the thing, if you have logs on each side, you can untake the log. Just like you take the log to get the exponents to come down to solve some problems, you can untake the log in this case. If they're like base logs, the log of this side, the log of that side, you can undo or do anything to, as long as you do it to both sides of an equation. So that helps us out. And then we have this simplified problem now we can see to work. And we use our old algebra skills here to distribute the 2. 4x plus 2, 3x plus 4. That's a linear equation, you'll be happy to know. So we bring the x over, makes a total of 1 x's on the left. Take the 2 to the other side. 4 minus 2 is 2. X equals 2, potentially. You always have to look back at the original problem and say, can I plug 2 in for all these x's? And it keeps the argument of the log still positive. And it does. That's really what we're looking for. 2 times 2 is 4, plus 1 is 5. So we can take the log of 5 plus the log of 2. And you could do that in your calculator since it's common wouldn't be as work. And see if it's saying as log of 3 times 2, which is 6, plus 4, 10. So is the log of 8 plus the log of 2 equal to the log of the log? Take that away and it will work out. Okay, another problem similar to that, this number 17 example. We also have an expanded log form. Now we get to do one with the minus sign like I mentioned earlier. Like base logs, so these are all base 12 logs. Most of your homework, I think all of them have like base logs, so you'll be able to work it with this method. But that is critical that these would be the same if that would ever jump out as a type of problem. You cannot work it if it did not have like base logs. You'd have to fix that in some way. But our homework will, and then if you have a minus with like base logs, that means divide. You can condense it to divide. Log base 12, and you'll divide these two arguments. X minus 4 over x plus 5 equals log base 12 of 3. So now that we convinced it to just log on this side, log on that side, you can undo the logs or kind of just wipe that out, and then it leaves just the algebra problem that we can work based on our old set of skills, old algebra. All right, so how are we going to solve that? I don't know that we've done one like this in quite a while, so it's a little harder. It's not straightforward linear, and it's not quadratic. So we've got to get rid of the fractions, the first thing. That's what's different about this. Anytime you have an equation with a fraction, step number 1 is to clear the fraction. So we want to times through by this LCD of x plus 5. This is over 1, you might notice. So this is the LCD. So you could do it like that. And it would be the same thing as this little shortcut, which is just cross multiply. You have a fraction equal to a fraction. The cross products have to be the same, right? So we can cross multiply x minus 4 times 1 equals 3 times x plus 5. And then solve that by distributing the 3. Bring your x's to the same side. I'm going to bring my x to the right side this time. That'll be 2 x's on the right. The 15 other way, negative 19 there, divide by 2, and I'm getting x is negative 19 halves. Now we'll have to see if that works or not. You know, sometimes even though the algebra works out, it's beautiful algebra and no mistakes in your work, it just doesn't work in the original problem. There just isn't anything that would work, and I think that might be what's happening here. Remember, you can't have a negative argument of your log. there's no base to any power that equals a negative number. So negative 19 over 2 minus 4, it's even going to be more negative, right? So that's not going to be a positive number, so we can't use it there. And I think it's the same case here. You know, negative 19 over 2 would be negative 8.5. Negative 8.5, even though you've got a plus 5 to make it a little less negative, it does not overcome the negative number. You'll still be at a negative. So there's no way to get this problem to work out. You'll get an error reading when you type in the log of a negative number. So we can't use that beautiful answer we worked so hard for. So the answer is actually no solution. We had no other alternate solution to try. So what we had didn't work, so nothing works. There's no solution on number 17, or at least on this example. You know, yours, it regenerates out different values, so you always have to check your problems and see. All right, I need to find another problem. Those are the only ones I had readily listed for you, so just bear with me for just a second. I'm on number 18. Number 18, it's going to be very similar to one we've done, so I'm going to go to number 19, a sample 19. Sample 19 has the formula. We've seen this before in an earlier section. It's the compound interest formula, and we're given some values on this one sample problem. It says, how much will there be in the account at the end of 10 years? So it tells me time is 10. Is 10. If $7,000 is deposited, so my p-value is $7,000 deposited at 3%, that's my rate. Sorry there, I'm all over the place. 3% rate. And then it tells me compounded quarterly. That's what this N means. It has to tell me how it's compounded. This is the compound interest formula. If quarterly, that means 4 times a year. So we'll use N as 4, and you use it for both of those. So again, quarterly compounding means it compounds 4 times every year. So this one is a direct push into your calculator. Change your 3% to 0.03 divided by 4. And 4 times 10 up there, let's go ahead and call that 40. We'll type that directly in our calculator to get that. And there's no algebra really needed in this because everything is known on this side. So parenthesis 1 plus 0.03 divided by 4, close your parenthesis, and raise it to the 40th power. 9,438 and 44 cents would be our answer there. All right, then it's going to ask me about this equation in different ways. It's going to ask me to solve for time now. We haven't been able to do that before. So let's see, number 20. Yeah, number 20, we're using kind of the same idea, only we're solving for time. And again, we couldn't solve for time before completing this section because we couldn't solve for exponents. That's what logarithms allowed us to do in this section. So this problem says basically you're starting out with $28,000. That's your p-value. It's at 4%. That's your r value. Compounded quarterly again, so that's 4. And we don't know t. We're going to solve for t, and we want our money to grow to $32,832.20 to be exact. So we're going to have to work backwards. This is going to be a little different for us to solve for the t value. So the first thing I'd recommend, now if you're thinking about just multiplying that together, you cannot because exponents come before multiplication in order of operation. So we're going to have to work backwards on this. Now you could go ahead and type that in your calculator. That won't hurt. Let me go ahead and see what I get. 0.04 divided by plus 1. Parenthesis is 1.01. If that kind of makes you better. But, like I said, you can't actually directly multiply the 28,000 times that 1.01 because we're stuck. You have to do exponents before you can multiply. So we can't work it directly. We're going to have to equation solve. We're going to have to do our work backwards equation solving. So I'll divide out the 28,000. That won't hurt anything. I'm allowed to do that. Divide by 28,000. I'm going to get one of those awful decimals again. So we'll try to keep that intact. But let me just show you what it would look like. It's 1.17257. It's an irrational number again. So we don't want to We don't want to do that, or at least it's a long decimal, so we don't want that. We want to leave it intact. 32832.2 divided by 28,000. And just think of that. We'll work that out in a minute. Okay, here's where we're at. The other side, though, we've simplified to 1.01 raised to the 4t. So I want you to notice this takes us back to exactly where we were in the other problems. We have some sort of base, no exponent here, although it could be, and then another base to an exponent. So how do we solve for the exponent? That's by logarithms. So we always want to work the problem down, simplify as much as we can before taking the log, then take, and it could be log or ln, a logarithm will bring this exponent down so you can work this. So we got the log of this complicated decimal amount, which we'll type in and keep it exact as we can in a minute, and then 4t times log 1.01. To finish our process, we need to divide by all the things around our variable. So we need to divide out the 4 to get the 4 to cancel, and divide out log 1.01 to get that part to cancel. That will leave us t equals. So do the same thing to the other side. Divide this side by the 4 and the log 1.01. Now, talk about difficult to get in your calculator. We're going to need a parenthesis around the numerator, so a double parenthesis happens here, and a parenthesis around the denominator, and we'll need a parenthesis around the argument of our log. So carefully typing all that in. Let's see if we can get that to happen here. So parenthesis to start, then we do log, and it brings up the parenthesis, 32883.2 divided by 28,000. Close, close. Then divide that all by the denominator. 4 log 1.01, close, close. Almost exactly 4 years. You see how it's 3.99999, depending on what they tell you to round to. Pretty much always it's going to be whichever place. There's so many nines, it's going to round up to 4. So our answer for 28,000 to grow to 32,000 something, it takes 4 years time for that to happen at 4% interest compounded quarterly.